Hello everybody, welcome back. This lecture is about the module 3C. So last two lectures, we discussed about what we have to study to design or see what the desalination plan and what's the key terms and what the quality parameters, introduction to reverse osmosis. So this lecture is about how to design of RO, so we can have a further detail of the designing reverse osmosis. So we studied last lectures RO membrane, how we can produce, and then what polymers, what kind of layers, and this time we can focus on more about element. So already we mentioned about spiral wound RO element last lectures, and standardization in element design. We can select some of the different element. So PW 4040. So brackish water 4" and then 40" which means the first 40 is 4" in diameter. It's almost 10 centimeter of diameter and 40" in length. So this is 1 meter of length of the element. And then SW 2540 means seawater SW 2.5" in diameter, so almost 5 centimeter, and 40" in length, 1 meter length. So depending on your water capacity, so we can select 8", 4", 2.5" in diameter, and mostly length is very similar, 40", 1 meter of length, and this can be a basic element. So this is very compatibility is high, and then pressure vessel and cap, and every company they follow this strong compatibility standard, and we can utilize any different membrane element to operate your RO membrane processes. And simple design, also research and development benefit all end users and manufacturers. And bad thing is the lack of diversity. So in the future we can improve the diversity of different elements. So let's look at a video of our element. So this is from the Dow FilmTech Corporation. So you can better understand how to fabricate our element, and then how we can apply for this element to design our seawater desalination plant.
FilmTech Corporation, a subsidiary of the Dow Chemical Company, is the world's leading manufacturer of reverse osmosis and nanofiltration membranes. Our products are used in a wide variety of industrial, municipal, residential, and commercial applications, helping Dow achieve its mission of improving what is most important in life, the human element. Our cutting-edge manufacturing technology improves the performance and quality of our membranes and provides the scale and infrastructure to serve the rapidly growing demand for RO and NF membranes. Providing high-quality membrane products starts with quality raw materials from ISO-certified suppliers. FT30 thin-film composite membrane, invented by FilmTech nearly 3 decades ago, is the genesis of today's industry standard. With each new generation of manufacturing equipment, the quality of FilmTech membranes is continuously improved through advanced process automation and control, from handling polyester-based material through casting the microporous polysulfone support to the complex polymerization reaction that creates the polyamide membrane layer. Design innovations allow us to use advanced membrane recipes that improve membrane performance and consistency. Dozens of critical variables are controlled and inline quality checks are performed to produce consistent, defect-free membrane without patching, and giving FilmTech membrane the widest pH cleaning range in the industry. A spiral wound membrane element can be fabricated manually or automatically. Dow uses custom-designed precision rolling equipment to automatically fabricate FilmTech elements because it allows for better, more consistent element performance. Sophisticated robotics for leaf construction and assembly ensure that every element is precisely built without membrane damage that often occurs during manual handling. Automation enables construction of more shorter leaves compared to manual rolling, resulting in a more efficient product that is less prone to fouling. Precise computer-controlled glue lines ensure the highest active area in the industry with guaranteed accuracy and minimize leaks, which can result in poor permeate quality. FilmTech elements are optimized to have the highest active area combined with the thickest feed spacer in the industry, offering several operating benefits, including improved cleanability, lower pressure drop, increased durability, and the ability to handle more challenging feed waters. A unique barcode allows continuous tracking of each element. Online quality checks for scroll integrity and dimensions and an inline vacuum test are performed on every element to ensure mechanical integrity. Any elements failing preset measurements are discarded. End caps are welded to the product water tube in a process that improves element strength, and a quality test ensures weld integrity. Our automated fiberglass process ensures exact and uniform fiberglass application within controlled dimensional tolerances. To validate final element performance, FilmTech uses both a traditional 20-minute performance test and a groundbreaking pulse integrity test, which has the unique ability to detect and diagnose mechanical defects. Tests are computer-controlled, and elements not meeting defined test ranges are discarded. Custom-designed packaging equipment combined with precision-injected preservative ensure protection for elements during storage and transportation, and easy handling. Prior to shipment, product for each customer order is scanned for traceability and to validate all previous quality checks. Quality is built into every FilmTech element, from the management of raw materials to final shipment. Every element undergoes multiple inline quality measurements, and additional parameters are measured based on defined sampling plans. Our technology enables a robust, consistent, defect-free membrane with the industry's widest pH cleaning range. Automated precision fabrication enables elements with maximum guaranteed active area, the industry's widest feed spacer, shorter membrane leaves, consistent high-integrity construction, and ILEC interlocking end caps. Collectively, these features enable consistent, reliable performance of RO systems with reduced system capital and operating costs. With the infrastructure to meet the rapidly growing demands of the market and the technology framework for integrating future innovations, Dow continues to lead the industry in reverse osmosis performance and value enhancement. Our goal is to offer the best membranes to enable the highest quality water at the lowest total cost. Innovation, automation, quality. FilmTech.
So this video shows how to produce RO element. So there are more than 10 companies to produce this kind of RO element, and they have a different type of rejections, water flux, and different membrane surface area. So most of membrane manufacturers provide the detail of the your one element, how much surface area, how much water flow, water permeability coefficient. So based on this information, and we can get some designing parameter to select our arrow element and then membrane processes. So let's look at more detail how we design this arrow element. So first one is the pressure vessel. So pressure vessel consists of fiberglass or stainless steel to tolerate high pressure more than 60 bar, 70 bar. So we need a very strong materials, and up to 8 spiral round elements in one pressure vessel can be located, and vessels can be arranged into banks with desired number of stages or passes. So if you look at this diagram, so outside this is the pressure vessels. So inside pressure vessel, each element will be located here. So your feed water is passed through, and in between, so your seawater flowing this channel flow, and then you have permeate water flux can be collected from this product water outline, and then this is the keep concentrate, and then brine is coming out from this pressure vessel, and this pressure vessel required very high pressure, so you can design the very high strong material, and this can be a good kind of design, and that we can put around 1 to 8 elements in one pressure vessel. So depending on your design capacity, so we can select 7 elements or 6 elements. So let's look at the pressure vessels house. So what's the typical water flux distribution and then pressure distribution? So this is the seawater pass through this element, each element. So you keep increasing your concentration of your feed water, and then you can see the red color, which is the concentrate discharge point. And then when you have a high concentration of your salt concentration because of high osmotic pressure, so your flux will be decreased at the end of your element. So initially you have a higher flux, then lower water flux. How about pressure distribution? So we have relatively high pressure, and then you have a pressure drop, and then pressure will be lower at the end of your element, which means each element will have a different water flux, salt salinity, and pressure difference. So let's look at the one pressure vessel, 8 elements. So if you look at the salinity of permeate, so in this case, first element, you have a low concentration of seawater, and then high concentration of seawater. So rejection is basically same, so that your permeability salinity concentration is different. So you can see the first element, the permeate water concentration is around 150 milligram per liter at the end of the element. So more than 400 milligram per liter of total dissolved solid concentration is coming out. So we mixed all the permeate and then calculate what's the final concentration of our TDS. Also, if you look at the permeate flux, so relatively low osmotic pressure and high osmotic pressure, which means you have a higher flux at the first element. So you can see the 25% of the water flux can be achieved at element 1, and element 2 20%, element 3 15%, and then you have a high concentration of seawater and you will get the very low fraction of your permeate flux. So element 8, less than 5% of water flux is coming out from this element. So we have to calculate all the details from each element in one pressure vessel when you design your seawater design. Also, spiral module, we can have 8 perfectly identical elements, but how about operating condition? How this will change? And from what we know before, so first element, if permeate flux is too high, so what will happen? And last element, if cross flow velocity is too low, then what will happen? So we have to think about balance of the water flux in concentrate and permeate. Also design implication of the range for your seawater. So this slide shows the pressure profile of a practical system. So we have a high pressure pump, and then this is the first stage, and second stage, and third stage. In general, when you have a higher stage, so you can have a more high recovery rate. And this is the first stage, and high concentration goes to the next pressure vessel, and then last stage will recover more water. So if you look at the pressure profile, so driving pressure, initial stage, first stage is very high, and then second stage, because osmotic pressure increase, the applied pressure relatively lower. And finally, you will achieve the almost the maximum of your recovery compared to applied pressure and osmotic pressure. So we need to consider to achieve the highest recovery rate in terms of this osmotic pressure range and applied pressure. So this is the boost pump. So when you have a high osmotic pressure along with different stages, so you have a higher osmotic pressure, and you can install the boost pumps, and each stage you provide a boost pump which will increase your applied pressure, which can generate the higher water flux recovery. So this is the way how we can design boost pump to achieve the high rate. So when you look at the different variation of flow fluxes and concentration in one cascade. We just say train. And if you look at the different behavior, feed flow rate, flux, and feed side concentration. So feed flow rate decreased at the first stage and little bit increase at the second stage because they have a less number of element and pressure vessel. And then final stage you have also higher feed flow rate because of less number of element and pressure vessel. And flux range at the first stage highest water flux, second stage in the middle, and the last stage because of high osmotic pressure you have less water flux coming out, and then feed side concentration will increase when you have a higher stage. So when you see the first stage, they have a mostly colloidal organic fouling at the beginning of your element. At the last element, we have a high concentration of salt, and then this will create the scaling such as silica or insoluble salt like calcium carbonate, calcium phosphate, calcium sulfate. So we need to look at the water chemistry. Already we studied essential water parameters to predict what could be the inorganic scaling when you recover very high water flux at the last stage. So how we can prevent this scaling and fouling, so we can design better way of our RO module and element. So this is the excessive differential pressure, which can cause the structural damage and looks like membrane telescoping. So you produce a very high pressure unbalanced, and then your spiral round module. This is spacer, this is membrane, and then you can see there's some damage of our membrane element. Also you can see that some of the membrane fouling, dark color, will keep reduce the overall membrane element performances. So let's look at what's the design objectives and constraints, and then system performance, membrane operational constraints, and some more specific terminology such as first stage, second stage, first pass, second pass, and this can be utilized for design your own seawater desalination plant. The objectives are production volume, permit quality, system flexibility, variation in water demand, and downtime for maintenance, variation in feed water quality, and membrane utilization. So what are the constraints? The membrane constraints are element recovery. So we target 50% of water recovery in seawater desalination, and how we can distribute each recovery from each element. So initially different water flux, and then different osmotic pressure along with the membrane elements, and then this element has a different recovery. So how we can design all the differences, and feed water flows keep changing, retentate flow and permeate flow rate. So how we can make sure that they are balanced flow in these three different flow rates, and then we can produce the better design of this membrane processes. And differential pressures. So different pressure will create different water permeability, and how we can make sure that the constant water pressure, and we have to put the boost pump or some other tactics. And feed water parameters, free chlorine, turbidity or SDI, hardness, water temperature will affect for overall design of the membrane process. So let's look at the more detailed terminology in RO membrane element. So this is the spiral round type, and feed water, retentate, and this is the different design method. So this is very typical feed side, retentate, permeate. However, to increase the water recovery, we can partially recirculate our retentate to the feed water. So this will provide the better water recovery, because initial element and pressure vessel will have a relatively low concentration of salt. So we recirculate feed and then try to make sure that the water recovery is higher. Then when you go to the next element, so high concentration of salt can be discharged as a retentate. So we can also consider this way of the membrane. This slide shows the average permeate flux, combined permeate flow divided by the total membrane area in the RO unit. It measures the volume of water that pass through the membrane per unit membrane area in a unit time, so that APF in terms of LMH is equal to flow rate of the permeate here over membrane area. So we can easily calculate how much water flow required, and then how many membrane area, and what's the average water flux required for the. Also, salt passage is a percentage of permeate salt concentration to feed salt concentration. So SP is CP, permeate concentration over CF times 100%. So how much salt can pass through your and salt rejections is the percentage of the retentate salt concentration to feed salt concentration. So SL is CR over CF times 100, and 100 minus salt passage is the same function of salt rejection. So in seawater, 35 gram per liter. And then in general, the highest RO membrane rejection is 99.8%. So we can produce the less than 100 milligram per liter of salt permeate concentration. So we can calculate, depending on your feed water salt concentration and rejection, how much permeate concentration can be produced, to make sure our water quality. Water recovery is a fraction or percentage of feed converted to permeate. So recovery percentage is equal to QP over QF times 100%. So when you recover 50%, so you have how much water can be recovered from your permeate. So this is the very important design parameter, because it's relevant to your water chemistry at the last stage of element. so we can carefully consider to water recovery for the better design of the element. So this is the RO element. We have pressure vessel here, and this is the housing. So we just call this is the one of the train. So you can see the how many elements inside one pressure vessel, and then we just parallelly locate it. So in one squid, it consists of almost 16 pressure vessel. So we can design better way to reduce the space and effectively manage the what's the best way of the designing this. So let's look at the flow dynamics in RO element. So this is the one single element. So let's say feed water is 8 cubic meter per hour goes to the one element, and one element consists of around 12.5% of the recovery, and after that your retentate 7 cubic meter per day goes to the next element, and permeate has 1 cubic meter per hour. So let's look at the two elements in series. So rejection of this second element, recovery, and 0.125% of the recovery times 1 minus 0.125 here, so we will have 10.9% of the water recovery. So first element recover 12.5%, second element recover 10.9%. So next element will be less than this 10.9%. So each element has a different water recovery, and then all together we can calculate 50% or 40% of water recovery for seawater desalination. Also, RO system train is a single stage pass system, and second stage RO system, second pass RO system. So this is the feed water, different pressure buses, so permeate and retentate. We just call this is the single stage, single pass. So single pass, permeate, and first stage of retentate. So let's look at the second stage, two-stage RO system. Retentate of first bus goes to second bus. So this is stage 1, stage 2. So retentate from first buses go to the second buses, and higher recovery rate can be achieved, and the second bus receives a feed with the higher TDS and osmotic pressure. That's the reason why we can have a better way of the water recovery. So when you have a high concentration and concentration polarization is higher, and then we utilize the second pass, and then you have a salt concentration is mixed, and then your concentration polarization will be lower, and we can recover more from your. And this is the schematic of a three-stage RO train. So feed water goes to the first stage, 3 pressure buses, and then permeate and retentate can be collected, and this is the goes to the second stage and 2 pressure buses, and then we collect again, retentate, and then last pressure buzzer can be combined. So if you look at the concentration variation, so feed water 1.1 gram per liter, flow rate 840 cubic meter per hour. And first stage, after first stage, permeate flow TDS concentration 12 milligram per liter and 468 cubic meter per hour, and combining with this second stage permeate flow 60 milligram per liter 196 cubic meter per hour, and then goes to the third stage, and we have a higher concentration of salt 240 milligram per liter 51 cubic meter per hour. So all the permeate collected, so final average permeate concentration is 40 milligram per liter with 715 cubic meter per hour. So we designed 85% of recovery at the initial concentration of 1100 milligram per liter. So this is the average 20 LMH water flux, and 7, 4, 2, 3 stage design. So final concentrate is 7,460 milligram per liter, and then 125 cubic meter per hour can be designed from this wastewater reuse plant reverse osmosis drain. So seawater can be also designed such a way, first stage, second stage, and then watch the different breakdown of the concentration and flow rate, and then watch the recovery rate, average flux can be designed for your seawater desalination. Let's look at the two pass or second pass model system. Permeate of first pass goes to second passes. So this is blue line is the permeate from first stage, and first pass goes to the second pass. So higher permeate quality can be achieved because this is the clean water, and then another RO membrane filtration, and we have a better water permeability and then quality. So applied when RO membrane rejection is low and permeate does not meet the target quality. So we have drinking water quality. Total dissolved solid concentration is 500 milligram per liter. Sometimes when you have a very high concentration of feed water, TDS is more than 500 milligram per liter. That's the reason why to meet the target water quality, so we can go through the one more filtration, second pass, and then we can make a clean water quality. Another reason to utilize the second pass is specific target compound. First one is the boron. So boron concentration in seawater is generally 5 to 10 milligram per liter. However, boron is the neutral charge, which is very difficult to remove boron concentration. So that after boron concentration 5 milligram per liter, and then we have still higher concentration 3 milligram per liter, and then this concentration has to go through another filtration, and then finally we can get less than 0.5 milligram per liter of boron concentration. So in your assignment you have also strategic for the boron concentration removal. So we can simply utilize the second pass to improve the overall water quality. Also bromide. Bromide can combine with the chlorination and then produce the carcinogenic compounds, bromate. So that we have to reduce the bromide concentration in feed water, and then second pass can reduce our bromide concentration, which is useful for the final concentration of our permeate target water quality. So second pass can be used for target water quality satisfaction. So let's look at the energy distribution in seawater desalination plant. So this is the overall total energy usage. 3.9 kilowatt hour per cubic meter required to desalinate the water with the TDS concentration 35 gram per liter and temperature 23 degree. So intake from seawater, we collect seawater, so we need to pump. So this will consume around 0.2 kilowatt hour per cubic meter. And this goes to the pretreatment, filtration or sand filtration or ultrafiltration. So we need pumping and pressure. So 0.4 kilowatt hour per cubic meter. So almost 10% of the energy consumption in the desalination plant. After pretreatment, we need a high pressure pump to operate the reverse osmosis system. So this RO requires 2.8 kilowatt hour per cubic meter of the energy consumption, which is equivalent to 72% of energy consumption. And after pumping, so we have to deliver this water. So pumping energy consumption is 0.3 kilowatt hour per cubic meter, almost 8% of overall energy consumption. Also, we have other facilities such as the sludge disposal and then discharge to our brine, and we need around 0.2 kilowatt hour per cubic meter, 5%. So altogether 3.9 kilowatt hour per cubic meter. As I mentioned, this is so how to calculate energy. So we can see this kind of very simple example for our energy calculation. So seawater flow rate 100 cubic meter per day, apply pressure 75 bar, seawater desalination, auto recovery design 40%, foam flow is 40 cubic meter per day, and power required without energy recovery device. I will talk about the energy recovery device next slide. And so this is the energy recovery without. So we need a 300 kilowatt, and then we just divide by overall flow rate cubic meter per hour per minute flow, and this will lead to 7.5 kilowatt hour per cubic meter. So without energy recovery device, so this value can be calculated from your energy metering system. And power required with energy recovery turbine and energy recovery pressure exchanger, which will save your energy cost. So we just say 30 to 40% of energy saving, 50 to 60% of energy saving. So we can calculate around 3.5 kilowatt hour per cubic meter with the pressure exchange 4.4 with the energy recovery turbine. So this is basically we calculate from the energy metering system using pilot scale of RO membrane. But theoretically, also we can look at some calculation. Let's say 70 bar pressure applied, feed pressure, and 3 cubic meter per second of flow rate. Typical water for feed pressure for high salinity Point 8, pump efficiency and the consumed feed water energy, because most of the energy consumption in seawater desalination is from pumping cost. So let's say feed pump is equal to your flow rate, and this is the pressure applied, and pump efficiency. So 3 cubic meter per second, 70 bar pressure, the energy pumping efficiency 0.8. So we calculate this value and then convert your unit, and we calculate theoretically this pumping cost for RO membrane 7.29 kilowatt hour per cubic meter. However, we have energy recovery device, therefore we save the more energy from. So let's look at the overall energy. So this is the seawater RO system construction cost 31%, power cost 26%, intake discharge construction 11%, pretreatment concentration 12%, SWRO membrane replacement 6%, others chemical or sludge disposal 9%. So let's say this 100 kilowatt watt times 10 hour, we just say 1000 watt hour. So this is 10 light bulbs, and 100 watts utilize 1000 watts per 1 hour is equivalent to 1000 watt hour. So 1 kilowatt hour energy cost is almost $0.29 in Australia. So let's say 4 kilowatt hour per cubic meter desalinated water. Energy cost of Sydney desalination plant, so we produced 250,000 cubic meter per day. So every day we spend $290,000 per day for the energy consumption, which is very huge. That's the reason why all the desalination plant in Australia utilize the wind farm, which is the renewable energy, to reduce the CO2 and then the environmental impact. Also, to save the energy, we have a different strategies. So let's cover this energy saving technology. Already I provided your video and reading material for the energy efficient desalination, which is very important because energy intensive in seawater desalination. So this is the one of strategies internally staged design. So this is the pressure vessels, and we want to have a different element configuration. So we call ISD 36 combination with 3 different SWRO membrane. So this is the high rejection, and this is the middle rejection and lower rejection, and each element has a different characteristics, so we can try to optimize their water flux and rejection. So you can see the average flux 12 to 16 atm, and this is the high product quality can be produced when you have your combination of ISD. And also we have lower specific energy consumption when you optimize the ISD, because high rejection will have a low fouling tendency, and then when you have a high concentration polarization, so so you can have a high water flow, then produce your satisfaction of water quality and minimizing energy consumption. Also, we can utilize a split partial single pass. We just say SP arrow. So how to design this pressure vessel is another strategy. So you can see the feed water goes into pressure vessel, and we collect this permeate at the initial stage of the element, and then we just collect front permeate here. On the other hand, we just say split. So your concentration of feed water is high at the end of your pressure vessel, and your permeate quality will be also very high concentration. So rather than mixing to the low quality of salt concentration, we split, and then we just return to the feed water concentration, which will dilute your feed water and then produce the good quality of your overall permeate water quality. And then this can be utilized only one pass. We don't have to go through the second pass. Just the first pass is okay, and we don't need to go through the second stage. So this can be a first stage, first pass can be achieved to save the overall capital cost and energy cost. So if we apply this one, we can produce the high purity water production, low energy and low cost. So people believe 0.4 kilowatt hour per kilometer can be saved when we apply SPS. Let's watch the video on energy recovery device. The pressure exchange is one of the breakthroughs of the seawater desalination in RO process. So this really reduced a lot of energy. That's the reason why the RO membrane process is a dominant technology for our seawater desalination. So this is the example of post desalination plant to apply for pressure exchange energy recovery device.
It's crazy that a planet covered in water is running out of the stuff. That's why this is so important.
So what you're looking at here could be one of the most significant engineering breakthroughs you'll see in your lifetime. It's predicted that by 2025, demand for fresh water will exceed supply by more than 50%, leaving a third of the world's population without ready access to fresh water. But we don't call ourselves the blue planet for nothing. Our vast expanses of sea may well be our saviour. The process called reverse osmosis, where huge amounts of energy are needed to pump seawater through fine membranes which filter out all the dissolved salts. But as you're about to see, a simple invention has revolutionised desalination, and those high operating costs are no longer a major problem. While modern desalination plants are far more efficient than they were 20 years ago, they still use a whole lot of energy, most of which is wasted. On average, it takes 3 glasses of seawater to produce just 1 glass of drinking water. But you're still paying for the energy that it takes to process all 3. And that, ladies and gentlemen, has been desalination's Achilles heel. Despite their best efforts, scientists have not been able to radically improve that production ratio of seawater to drinking water. So they began investigating ways of harnessing the pressure energy of the reject seawater and using it to help power the whole operation. Californian company Energy Recovery Incorporated finally cracked the problem with a device called the PX pressure exchanger, which cut energy costs by a massive 60%.
So what the pressure exchanger does is it recovers the energy in that waste stream at almost 100% efficiency. It operates at 97% efficiency, which in engineering terms is extremely efficient.
John McHarg heads up the Affordable Desalination Collaboration, a US Navy joint project with the Bureau of Reclamation. For more than a year now, they've been testing and evaluating the latest desalination technologies, including the pressure exchanger.
With old desalination systems, you used to have to pump 100 gallons a minute to get 40. With the new desalination systems and this pressure exchanger technology, you pump 40 gallons a minute and you get 40 gallons a minute. It's amazing.
Yes, it really is that amazing. Just a ceramic cylinder capped at either end by fixed propeller-like end ducts, and all precision fitted inside a tubular housing. The pressure exchanger is effectively cutting running costs by more than half. And that's great news for cities like Los Angeles. So what does this mean for the future of the world's freshwater supplies? Well, in the city of Perth on the west coast of Australia, it means securing the future. It's about to become the first city in the world to use the latest desalination technology, including the energy-saving pressure exchanger. The $350 million desalination plant will be finished in time for summer next year, guaranteeing regular water supplies for the next 30 years. Back where the technology was invented, California, there are 6 new pressure exchange plants in the pipeline. Every day, the need for fresh water is challenging nature's capacity to produce it. So what you're looking at here could be one of the most significant engineering breakthroughs you'll see in your lifetime.
It's crazy that a planet
So already, as this video shows, the pressure exchanger is the one of the breakthrough to reduce the seawater desalination plant. So what happened is that this is the seawater, this is the ceramic rotation material, and seawater is flowing this way, and the other side we have a high pressure concentrate, almost a 60 bar, and then because of this pressure, and this will rotate this ceramic material, and then it's coming this seawater, and this pressure will push this seawater, and then this goes to your RO influent, and this will change your high pressure to transport to the seawater feed water, and then you can save your energy. So this is the way we can reduce our energy cost. And one of the small problem is that whenever they push it through, and then they touch a little bit of seawater at the surface here, so concentration is slightly high, but compared to the energy saving cost, so this is very marginal. So that's the one way of the pressure exchange currently applied in 3 desalination plants in Australia. Also we have different. So pressure exchanger is the most widely used energy recovery device. Also we have another energy recovery device which is dual works and exchange energy recovery. And likewise, this is similar to pressure exchanger, required just high pressure of brine here. This is the low pressure seawater, and we have some media here, and when you have a high pressure of brine, just push your low pressure seawater, and then this pressure energy can be transferred to this low pressure seawater, and this goes to your RO pressure pump. So this is the way you try to absorb your high pressure from the seawater, and then you can get the good energy recovery system. We can save energy from pressure center concept. So this is applied in post desalination plant. So you can see the high pressure pump, and this is the train membrane module, and then pressure exchanger, and then you can continuously operate this RO process. And when we have a high pressure pump, you can see how many train can be applied, possibly 5 other train. So depending on the pump size, so we can design different membrane train, so that the pressure center concept is related to we can make a bigger pump and then decrease the more pump number of pumps, and then we can have better pump efficiency overall. So we have this high pressure pump will increase the availability and reliability, high efficiency, and greater flexibility on the variable operational modes, which will ultimately reduce the capex opex cost. And this pump, in general, we utilize the horizontal centrifugal axial split high pressure pump with the optimized size in order to achieve the highest efficiency. So when you have a bigger pump, and then pump efficiency is higher, so when you increase the 5% of pump efficiency, we can save around 0.1 kilowatt hour per cubic meter. So this is the economy of the scale and the simplified erection, and then feed pressure to the RO train to be increased and decreased, and meaning that all RO trains remain operational during period of reduced. So we have also another skills to operate the desalination plant. For example, considering desalination plant initially operate and completely shut down because dam level increased more than 80%, 90%. That's the reason why, depending on our surface water resources, so we can try to stop because the seawater desalination is very energy intensive. So when you have dam storage level reaching to 90% capacity, the minister directed the cylinder desalinator to cease production on 1st July 2012. Also, when we have a low level of dam up to 60%, on 27 January 2019, the desalination plant commenced restart. So we have a shutdown plan and restart plan. So this is the another planning. Depending on the dam level, we can decide, and we need a 8 months restart period, ended on 27 September 2019, after which the plant is considered fully operational. So depending on your reoperation period, so we need around 8 months because we need to order membrane, we need to clean up all the intake, outtake, and then pipeline system. And then that's the reason why we have to consider what's the trigger point of the dam level. So in your assignment, you can describe what's the shutdown and restart trigger point in Sydney desalination plant, and detail can be found in this website, so you can refer to this kind of. So let me summarize the Australia's SWRO desalination plant. So we have 6 desalination plant. Mostly they are around 36,000 milligram per liter, and product water quality is less than 200 milligram per liter. Temperature is average 20 to 15 degree, and capacity is Melbourne desalination plant is highest 450,000 cubic meter per day, and depending on this drought condition, the Sydney desalination plant also planning to expand another 250,000 cubic meter per day. And RO configuration, partial 2-pass, advanced split pass, and then partial 2-pass, and this is the SPSP and partial 2-pass. Also they utilize the second pass, mostly BWRO, 2-stage and 2-pass system. RO recovery 45% for the first pass, and then second pass brackish water RO is around 85 to 90% of recovery rate, and energy recovery device, the pressure exchange and dual work exchange energy recovery from Sydney, Gold Coast, and Melbourne desalination plant. So you can see the total energy cost around from 3.6 kilowatt hour cubic meter to 4.2 kilowatt hour per cubic meter. In particular, our system energy consumption is from 2.4 to 2.9 kilowatt hour per cubic meter. So this desalination plant is the large capacity, but in the future we have also large city in near the major city, so we will have also more medium-sized desalination plant in the future, and then design of desalination plant is becoming important. Thank you for your attention, and next class we will discuss about how to design our reverse osmosis membrane using computer-aided software. Thank you.